we're looking at this course is what's called K-theory and C-star algebras, right? A priori, those are different things. But there's a certain amount of connection between a certain amount of connection between two subjects. Does anyone want to suggest a connection? Are you Justin?
Yes.
Okay. Do you want to suggest a connection between K-theory and C-star algebras? Why, for instance, some idea why they're both in the same course?
I have to think more about it.
Okay, good. Vincent, do you have any ideas?
I guess because K-theory provides structures and things we can study about C-star algebra categories.
Well, I'm not quite sure about the category. I mean, I guess that's one way. That's one way of looking at it. In fact, you're almost talking about you're almost getting into one particular aspect of K-theory and C-star algebras, namely the sort of classification. That if you look at a C-star algebra, then at least if it's what's called a well-behaved, it's what might be called a well-behaved C-star algebra, well-behaved simple C-star algebra. We have discussed briefly. It won't be on the exam, but I mean it's the classification of well-behaved C-star algebras has just very recently been finished. But it's important chapter of mathematics, I think. But it'd be hard to fit into a course in its entirety, 5,000 pages, with everything that's been written related to that, sort of steps along the way, the last 60 years. Goes back to the very beginning of the subject in 1943, paper of Gelfand and Neymar, 1943. Someone say yes? That's pretty slow. I thought you're supposed to be able to look it up quite quickly. Anyway, just look up Gelfand and Neymar. And Gelfand had already been talking about Banach algebras, commutative Banach algebras, and the idea of spectrum and Fourier, what generalizes the classical Fourier transform. Called Gelfand. Have I mentioned how Gelfand sort of established the subject in the Banach algebra. Sort of all single major step. He found this Banach algebra proof, a short Banach algebra proof of theorem of Wiener. Have I mentioned that? Does anyone remember the theorem of Wiener? Talks about functions on the circle. And every such function has a Fourier series, not that the Fourier series converges. If it's an integral function. Continuous function, we might there's continuous function, then the Fourier series converges in a sense, but it doesn't necessarily converge uniformly. And but there's a special case in which Fourier transform, Fourier series converges uniformly if you look at the Fourier coefficients. So they're labeled by the integers, right? Fourier coefficients are numbered by the integers. By integration against power of z, function z and z equals z. Z to the nth, you integrate that, you multiply that by this function. You integrate that, and that's the Fourier coefficient. Whether you take plus n or minus n, well, that's case. But you have the Fourier coefficients. Well, the very important property of them is that they be absolutely convergent as a series. If you add up the absolute values of Fourier coefficients, you got a finite number. And these, I guess, are called well, there's a name for such a function, continuous function, Fourier series, absolute summable. It's called the absolute summable Fourier series. And, because the absolute value of the nth term, since the exponential function has absolute value 1, the absolute value of the nth term is the same as the absolute value of the coefficient. If you look at the absolutely summable Fourier series, you know that, of course, would be a continuous function. And, the question is, and these things form an algebra, and the question is, you have such a function, and it's not zero anywhere on the circle, it's a function on the circle, right? Well, if it's not zero anywhere, then you can invert it in a sense. You can, well, you can invert it as a continuous function. The pointwise inverse. You take the inverse of the values of the function. One function is f, you can call it 1 over f. Right? That's a continuous function. Question is that does that have an absolutely summable Fourier series? Okay, so that's a good exercise using this theory of unit algebras, which you're free to look up. So that's the kind of hint. I mean, Gelfand pulled it out of thin air, and that was kind of a miracle. But once one person has done something like that, it's like once one person has discovered North America. Well, okay, actually, I was going to say that it's not such a big deal when someone else does, but that's not quite true, is it? Through the centuries, different people have discovered North America. Discovered it, in a sense, coming at it from both sides, because it's quite complicated. Huh? All right. Well, interesting to trace the history of algebras. How far does it before Gelfand does it go? Banach looked at Banach. He certainly looked at Banach spaces. He didn't call them Banach spaces, but he called them B spaces. Okay, but certainly it's history of about 100 years. Both for algebras, either concrete algebras of operators or just abstract algebras. The norm known Banach algebra. So they bring theory quite closely related to the theory of algebras of operators. Well, and then K-theory growth, and then that's been well, quite to a better finding history of fairly intricate history of well, first in operator algebra, theory of operator algebras, and then in the geometry of this algebraic surfaces. Algebraic geometry is studying these zero sets of polynomials, right? That's the polynomial. That's a rough summary of algebraic geometry. We would see now. Descartes had the idea that you should, instead of studying spaces, you should study the algebras of functions on the spaces, and I think that's what was one of innovations that Grothendieck a lot of innovation. I think because of his background in operator algebra theory, discovered that what he called K-theory, very helpful tool in studying the algebras arising in geometry. Then T and Hirschberg noticed that this could work just for topology too, where you're not looking at that's great structure. And this again more or less interpreted in terms of algebras, more or less equivalent, pretty clearly equivalent to looking at certain algebras, namely the algebras of continuous functions instead of algebraic functions. Grothendieck looked at continuous functions. Well, so that's a commutative mathematic algebra. Commutative C-star. Gelfand and Neymark had put on an axiomatic basis as part of their axiomatization of general C-star algebra. Which arose first as concrete algebras of operators on a Hilbert space, and then once you had them on one Hilbert space, they were often crying out to be represented on a different Hilbert space. People got the idea of representing, of characterizing them abstractly, just an abstract algebra, abstract star algebra, if you like. And Gelfand and Neymark lead in that, finding simple axioms. Make sure that abstract star algebra is isomorphic to topology. But somehow it turned out that K-theory not only did it was soon after T formulated by periodicity for the terms of the algebra. As discovered, however, in there with like systematized. But then it was noticed that this worked just as well for a non-commutative mathematic algebra. And then it was noticed that for C-star algebras, this was almost the only, I think I might have put it this way before, it was almost the only game in town. That's getting back full circle to the well-behaved, simple C-star algebras. Well, you have to agree that what my last 10 minutes is more simpler than 5,000 pages. Right? But, well, and it just happens that the straightforward case theory information determines these algebras, and you can even express it as Vincent suggested in terms of a functor. K0 is a functor and K1 is a functor. And the tracial simplex, the unital algebra, or the tracial cone, if it's not unital, the tracial cone, the traces bounded or not, is defined finite on a dense set of positive elements. It's not finite on all positive elements, then it doesn't quite make sense. Finite on elements that are not positive, because you end up subtracting infinities. Notice for operators on Hilbert space, how many people have come across the idea of the trace of an operator on the Hilbert space? Yes, good. It's a class of operators, positive operators called trace class. Well, in the first instance, positive operators. Positive operators. And extended trace class operators form a subalgebra effect an ideal. It's like a compact operator. It's not a normal, it's ideal. It is a Banach space, so it's a certain norm. Every Banach space has a dual space, right? Okay. If you have a Hilbert space, what's the dual space? Yeah, in a strong sense, it's the Hilbert space itself. Actually, it's the opposite Hilbert space. In the real numbers, real scalars, there's no difference between the Hilbert space and its opposite. But in the case of the complex Hilbert space, the opposite Hilbert space, you flip the inner product. And that's one way of saying it. Or you flip the complex, well, at the same time you flip the complex multiplication. Multiplying by I in the opposite Hilbert space is the same as multiplying by minus I in the original. So, and you have to say that because there's been a canonical isomorphism between the dual of a Hilbert space, the Banach space dual, complex Banach space dual of a Hilbert space, and the opposite Hilbert space. Not so much the original Hilbert space. Of course, in the real case, it's the same. Well, that's an example of Banach space developing in setting Hilbert space. But another example is when you take the dual of the Banach space of trace class operators. You might want to try their luck what this is. Are you?
Solid.
You're set.
Solid. Solid.
No. I'm just terrible with things. I should go through. Why don't I go through the names? That's I'm doing a little thing. Okay, so and you can tell me when I get to you. No. I'm very. I mean, I try to make it not look like it, but I'm very embarrassed. Okay. Hussam Andrew, Abigail Arsenal, I think. Jack Cerrone. Okay. Yuja Cheng. Okay. Carissa Chowli. Okay. Arka Prava Chaudhuri. Siddharth Daga. I mean, some people I know that they're very often here, and then some people I haven't even met. Right? I don't think, but Daniel Dima. Yeah, Dustin Fuchs. Is that a good okay pronunciation?
Plus.
Plus, okay. Savek. Trouble is, I get exposed. I travel too much, and I get exposed to languages in different places, and then I try to imitate the pronunciation, except I don't know which one to imitate. And Savek Germanic.
Yeah.
Okay, that was you. Okay, you know, I was going to say Savek if I didn't say it, but trouble was that's not the right pronunciation.
Yeah.
Yeah, I'm sorry. No, Charles Griffin. It's like I think it's almost a bit like computers. I mean, 50 years ago, didn't have to learn about computers. Well, 50 years ago, almost everyone you met had grown up and then gone to the same school as you, and it was a smaller world. Ken May Glover. I was thinking. And one. Yes, Vince, yes, thank you. Jalal Casa. Okay, thank you. Alexander Cole. Howard Chang Lin. You're going to get to know people's names better than me. Sure. And Juan V. Loke. Matthew. Ife Lu. I don't want to dun people, but the two people I just just mentioned, haven't given me any homework yet. So, and who does the homework hurt more? Sorry? Well, I just checked, and the number of people on Quercus is still 28, okay? For undergraduate section. Two graduates. More undergraduates than has been for a while, and fewer sometimes graduates. It started out as a graduate course. Luke McCutcheon. Oh, thank you. You know, I knew who you were. I knew your name, and I was going to ask you. Well, you're not the person sitting far in the back, but I was going to ask you if you had a reason. You want to avoid getting asked a question. Tell me you should sit in the middle. I'm sorry. Do you have a question?
Not right now.
Okay, but you have an answer to my question at the beginning. Any kind of an answer of relationship is part of discuss. Part of review. One has instance category. And you have a map between inclusive values, you get a map between or any function, you get a map between values. In the case of K0 and K1, the groups, and then in the case of the tracial cone. Well, if you look at affine functions on the tracial cone, then that's a vector space, or dynamic space. And again, it's a forward function. Covariant function. That's theoretical in nature, I would say. It's determined by the algebraic K1. You know about one might want to look at a paper of mine called K theory and traces. It's last couple of years, 3 years. And nowadays, you don't have to know anything more about. Okay, so did I get your name yet? We're about halfway through. Are you in the first half or the second half? Well, what letter does your name begin with? I should know your name, but if you're in the course, well then, okay, well then I'll come to it. You're not you say. Can I ask your name? Oh, right. Well, okay. Well, now I remember you. Now Shang Lin.
Yeah.
In fact, that was one of the very last names that I missed. For what it's worth. Abu Mohid. If you have any questions about the course and about the subject of the course, there's C-star algebras on the one hand, K theory on the other hand, and we're supposed to be talking about both, right? It's somehow it's like the question: can you put the following two words in the same sentence? Well, the one way of saying it maybe is that K theory helps to study the structure of C-star algebras and classify them. You can see already from matrix algebras and infinite tensor products of matrix algebras and the inductive limits of finite direct sums of matrix algebras. So those are all classified by K0. Okay, we will start again. Wonderful. Appreciate progress. See you, Mohammed Raza. The right side. Thank you. You're going well. Probably going well. You can well. It almost seems as if a number of people are deciding informally to withdraw from the course. By the way, what does staying in the course, what does being in the course involve? Well, recently, marks for the course haven't been due until a month after the end of term. Okay, so what I'm hoping is that I can extend that much latitude to people this time too. I'll have to clear that with Joshua Lau. He's been very generous. Well, this time adds up to a fixed amount just now.
I was just gonna ask.
You have a suggestion?
Well, yeah, I was just gonna say, like, is there anything more to it? The fact that K theory is just like a functor from category of algebras, category of.
Yeah, well, that's what it is. You can say the category of abelian groups, and it's not the if it's the these classifiable algebras are sometimes called classifiable algebras now. It's such a tight unit. This well-behaved simple C algebra. You only need the groups. You don't need the order structure because that comes from the traces. If you look at the traces, then those are basis of affine function on the tracial simple. Tracial state spaces, space of tracial functions, or one. Well, you have a projection, then it gives you an affine function on the trace space. That gives you an order relation. If you want, it gives you an order relation on the projections that people sometimes consider without even mentioning traces. In this well-behaved simple case, you don't need to look at the order structure separately. Just keep track of the fact that K0 maps into the affine function of the spatial. So, for instance, if you have matrix algebra, and there's a unique trace, so the spatial simplex is a single point, and the affine functions, affine real value functions are just real numbers. And if you have a projection in the matrix algebra, or in the matrix algebra over the matrix algebra, then it has a trace, right? And furthermore, two equivalent projections are going to have the same trace. The equivalent projection says one of them is x star x, some x, and the other is x star. And the trace is exactly the same one on two elements, x star x and x star. So then your function will have the same value. Okay. And this turns out that the K functor is one of the is almost the only functor on the C-star algebra which has certain simple properties. I won't go into the exact properties now, but they're quite elementary properties. So, if you well, maybe I have to go into them. If you tensor with the compact operators, it doesn't change. Okay? And it's homotopy invariant. You have homotopy between two algebras and compatible. And also it's what's called half exact. And in the 6-term exact sequence, what you see first before you worry about the index maps connecting the K0 probably in the K1, you have the map for K0, you have an extension, the ideal and the big algebra and the quotient. Then you map, have a functor, you map map a functor on the ideal into the functor on the big algebra, and then onto the into the functor for the quotient. And the middle of those 3 terms, you have exactness there. Okay. Well, first of all, the function we're talking about, if you do both of those maps, the ideal, the algebra, and the algebra quotient, level of the algebra, you get 0, right? You map the ideal into the algebra and divide out by the ideal, you always get 0. Start with the ideal. Well, the functor has that property. Actually, if it's a functor, then it has to have that property. Because the composition of the 2 maps from the functor has to be equal to the map coming from the functor from the composition of 2 maps, which is 0 within the extension. And then it's not a big surprise that the functor take a 0 map between groups into the 0. The 0 map between algebras and 0 map between groups. Yes.
Does that mean like if the K0 functor is like that.
No, well, the
K-theory
two things really go together, especially in the complex case. One is suspension of the suspension flips. Okay. They really should be, we should talk about K star, K0 and K1 unit. By the way, good reference to someone who's here this fall at Field Institute. He's the Simon English professor with the Field Institute in the operating algebra program. By the way, not next week, but the week, not next week, but the week after, there's a meeting, a workshop at the Field Institute. And, Professor Klein will be giving a series of 3 lectures. See, there's a Field Institute has a lecture series called the Coxeter lecture series. Everyone recognize the name Coxeter? He came to the U of T about 100 years ago. There's a picture of him in the Fields Institute, sitting on top of the piano, and it shows him at the kind of age where you'd expect the picture to be a picture of Mozart. Reminds me of well, I shouldn't digress much. Reminds me of another person and a couple of people, well, Kaplansky from here, and then Tom Lever, who was almost from here, because I think he probably student of Kaplansky, Harvard. It's worth looking up Tom Lever's work. Not as well. I don't know about his mathematical work, but his artistic work. Quite subtle. At one point, he was and he was musical because he accompanied himself on the piano. So his stories were sung. Have I mentioned him before? There's a particular you get some pattern before or after song. One of them, he happened to be comparing himself with Mozart, and he said, when Mozart was my age, he'd been dead 3 years. That's all. Okay, so maybe I'd like to say more about these 5,000 pages, the classifications of well-behaved. Just
Sorry, I have a question. You're talking about the role of races.
Yeah. Yes.
Is that, do you take a projection and you take the trace of that? Would that be the rule?
Okay, I left that open, right? Okay, do you have a suggestion?
Yes. So you can take the traces operator. And
Yes,
then,
yeah, you have the trace class operators. Let's just review what they are, okay?
Okay.
So they're self-adjoint and positive, which means that since they're also compact, they have when you look at a definition, it doesn't say it has to be it's a consequence that they have to be compact operators. So let's say it. Certain compact operators that are self-adjoint. So if they're self-adjoint, they're diagonalizable, right? Unitarily equivalent to diagonal compact operators. That means the eigenvalues on the diagonal go down to 0. And that's your operator. And if it's positive, then that's the same as saying that the eigenvalues are positive. And saying its trace class is equivalent to what?
It's
some
convergence.
Yeah, some convergence, yeah.
Yeah, so if the trace is reasonable, it should just be the sum of the diagonal.
Yes.
And you want that to be finite. Okay,
Yes.
so you have positive eigenvalues sitting down the diagonal.
Yeah.
If the sum is finite, then it's a trace class operator. That's a definition. That's a good definition. So, okay. And then you can extend it to the whole linear space if you want. But that's just because that's what we're talking about. And by the way, the norm for the positive one is just the sum of the eigenvalues. That's the norm. And if it's again, you can extend it to the non-positive ones too. Okay, but so it's a Banach space, not norm. And so what's the dual?
I was thinking you could take like finitely many diagonal entries and have them on scale though.
Well,
Any combination. That's one.
let me mention one property of these trace class operators. Compact operators are an ideal, like two-sided ideal. Well, it's true for the trace class operators too. I mean, you have an arbitrary operator, and you multiply it by a trace class operator, then you get another trace class operator, right? Well, it has a trace. So that means if you have a fixed trace class operator, then you get a linear functional on all operators, all bounded operators, by just doing that. You multiply and take the trace. Okay, so that's I can see a beginning relationship with what you were saying. Okay, because if you look at part of the diagonal, and that's cutting down by
The
projection.
idea was to like do like a projection.
Yeah. So if you want to know what your function is on if you take your projections on the diagonal, arbitrary ones and zeros down the diagonal, then that's just the trace of the product would just be the sum of certain eigenvalues, right? Okay, yeah, that's sort of what you were suggesting. Yeah, well, that's an arbitrary continuous norm continuous linear functional on the well, hold on. Actually, we're talking about it's a linear function. It depends on two operators, the bounded operator and the trace class operator. And what I meant to do was consider it as a linear function on the trace class operator. That's what we're doing. Okay, then it's a continuous linear functional in the sum of the eigenvalues is less than equal to the sum of all of them, right? Sum of them less than equal to the sum of all of them. They're positive. And so that's what the dual is of the trace class operator. It's the algebra, it's the base space of all bounded operators. And furthermore, if you look at you get linear, if you fix the trace class operator the way I was thinking of, and you then get linear functional on the bounded operators. Well, this is an arbitrary, what's called ultra weakly continuous functional. Any phenomenon algebra has a pre-dual. It's a dual of some Banach space, okay? And that's unique. It's a unique Banach space, and duality is really the norm, and everything is just as unique as it could be. In the case of B of H, in the case of algebra bounded operators as a Banach space, it's pre-dual, just a trace class operator, okay? And so it's a quite structured. Oh, okay, so no, thank you for the question, for the suggestion. Any more questions? Yes.
I guess my question was like, it's like, how exactly do we think about like infinite dimensional trace space, and how does that have to do with like, it's like, how do we like extract information? Because like in some sense, the trace state in infinite dimensional is like, say the C-star algebra above is like, it has no finite dimensional representation or something, right? Like it's like how do I look at infinite dimensional trace space?
Yeah, right. Well, that's a good question. Don't forget, for the case we're talking about the algebra of bounded operators, the trace is if you're looking at a positive operator, the trace is only going to be finite if it's trace class. If it's compact, and the sum of the eigenvalues is It's finite, okay, it's very, very special. But if it's a matrix algebra, then in both cases, it's a unique trace. For matrix algebra, every operator, if it's a finite dimensional Hilbert space, then the operator is there. It's the same as matrices in fixed spaces. It's the trace there is well, everything is trace class, and it's a linear function of everything. The norm behavior is still true. You look at the norm of the bounded operators on the finite dimensional Hilbert space, and that's the dual norm for the norm of the trace class norm. There are two norms on matrices, well, a whole lot of norms. One of them is the for a positive matrix, you take some of the eigenvalues, and the other is you take the norm. Those are quite different in norm. If it's a diagonal matrix, what's the norm? It's diagonal in an orthonormal basis. Well, go on. If it's one by you, always don't worry about being on the spot. But remember Helmholtz's dictum. Always look at the simpler problem. So if it's a 1 by 1 matrix, what's the norm? If it's diagonal, always diagonal, right? If it's 1 by 1, then what's the norm in terms of the eigenvalues? Well, it's equal, right? It's equal to the absolute value of the eigenvalue, right? Okay, that's true for any normal operator on a finite dimensional Hilbert space. But if it's diagonal, then you just take the absolute values of what's on the diagonal, and you take the largest one. And if it's an infinite operator, an infinite matrix, and you look at and it's diagonal, then you look at all the complex numbers on the diagonal, and if they're bounded, the operator is bounded, and the norm as an operator on the Hilbert space is well, there isn't any largest one, maybe, but it's the soup. Okay. But if people had done, someone had done all of the problems that Mr. Lau is suggesting people do, I bet you they would know this. That's the advantage of doing everything. And by the way, it's not quite everything, is it? He did everything. I'm not suggesting that everyone everything. Even just half the suggested ones, pick out depending on how you feel on a particular day, pick out the easy problems and do those. Next day you can pick out one of the difficult ones. Okay, but you're just looking at them and deciding which ones are easy, or which parts of which ones are easy, which parts are not. That's almost as good as doing them. It's certainly that's called beginning. That's how you begin. What I learned about an examination was that the first thing you do when you get the exam paper is look through it, read it carefully, read all the questions, because then you have all that extra time to think about them secretly, sort of automatically while you're doing the other one. I guess everyone knows. Okay, so getting down to the more specific question of block periodicity. It's true for the complex numbers, just like any other C-star algebra, Banach algebra, complex Banach algebra. And I was saying that it's not quite trivial for the complex numbers. In fact, there is a proof which is a little well, it's not really easier than the proof in the book for general Banach algebra. Okay? It's a proof which is special for matrices. I mean, of course, if you're looking at complex numbers, looking at anything, you have to look at matrices too, because that's how the K groups are defined. Well, the reason they're defined that way is that I didn't look at matrices to define the K groups, and you wouldn't have any such thing as block periodicity or index maps. So, specific question that came up was if you have closed curve vertical or unitary matrices. Special point is the closed curve turning it into say a unit. Then the matrix. And this is homotopic to one of the special ones coming from the projection. In the algebra itself, where you have to go to a larger algebra, you have to go to the matrix of the whole thing. Well, it depends what if you're trying to homotopic to p times z. This is just chalk I can throw out. I think, but how many people see that? Okay, so here p times z. Then you're never going to get well, that's an example of what you get from the projection in the algebra. Okay, that's close very good. But, you might also look at also look at okay, so you look at p times z to the n for some n, then clearly you look at one by one matrices. You're not going to inside one by one matrices over the complex numbers. The only way, the only path you get this way is just z. You get to z, and that would give you an arbitrary path up to homotopic. But if you look at z to the nth in the complex numbers, then it works. Okay, so that's the question. You look at a path, not just pz to the nth. Some production in the algebra. Now, it's still not true for an arbitrary Banach algebra, C-star algebra. And every closed path of invertibles is homotopic to one of these for some, even for some n's. Okay. But for a matrix, if you start with a matrix algebra with the complex numbers, then it's true. If you have a path in C, closed path of invertibles, beginning and ending the unit, then this is homotopic to a special one like this, entirely inside the algebra, okay? Which is not true for an arbitrary system. But so you might think it's easier. That's the main statement of what we just did, that every closed path, this is K, that's K1 of the suspension. K0 maps to K1 suspension. And then P maps to EZ plus one entity belongs to it. Matrix algebra. Okay. Well, so by the way, it's relatively easy. It's just one by one matrices. It's relatively easy to see that not everything is homotopic. Just take Z itself, and there's no way you can homotope that to a constant path in the circle. Just inside the circle. Inside matrices, well, I think someone suggested earlier. Take the determinant. I've forgotten who it was. Anyone? Someone hear me? If you take the determinant, and that gets you down to one by one matrix. And if it's invertible matrix, it'll be the determinant will be non-zero, right? So we have a path of non-zero complex numbers, and we know it will not be homotopic through such paths to a constant one necessarily. If it was, well, that means there are certain paths which even if you go to matrices, you can't hold it open to a triple. But, so that tells you that, the K0, it tells you that the K1 is, of suspension is non-zero. You get from that, K1 and C of T. If you want to get that, it's actually, it is just what you get from the Z function Z. K1 is just Z. Well, there's little Z and big Z. Okay, but then you have to prove that there's no surjectivity. Either that, or you do it in a special way just for a matrix. Okay. Well, the trick for matrices is quite simple to describe. The trick for the general Banach algebra is a little complicated. It involves linear algebra. Then you trade off. You make a polynomial approximation to the curve, and then you make the matrices larger, reduce the degree of the polynomial to a linear polynomial. Then you prove using functional calculus that the polynomial is linear, then it's just homotropic to this, what you want. Okay, that's how you that's how you prove projectivity in the general case. And by the way, injectivity is got is it's just an application. It's an application. It's described in the book. I'll talk about it again. But what do you do for matrices? By the way, I'm sure Mr. Lau will be happy to see people upstairs. By now, there probably could very well be room for everyone. That's a bit of an exaggeration, perhaps. Not that small room. But let me just say very quickly what the strategy is for a curve of a unitary matrices. Well, if it's a curve of unitary matrices, then you know that each one is diagonalizable. Each single unitary matrix is diagonalizable. And the eigenvalues may or may not be distinct, okay? But you can hit it a little tiny bit so that the eigenvalues are distinct. That's what you do to the whole curve. You hit it a bit, you kick it a bit. You kick the tire, it looks like a tire, right? So you kick it a bit. That's supposed to be something you're not supposed to do to your car. But you can do it here. You have, don't tell them I said. But, and then you get all the eigenvalues everywhere, at every point, at every one of these unitary matrices, except at the very beginning, where it's just the matrix. You get the eigenvalues to be distinct. Then you just trace them around think about it. This reduces the problem to the case that it's just complex numbers by itself. It's a single curve inside the circle. Okay, single closed curve inside the circle. Because you can always separate out. You can label the distinct eigenvalues. Continuous functions are always distinct except at the endpoints. So each one has its own identity. You can label it, and you just work with them. You can stretch them out so each one is a power of z. Okay, they're unitary matrices, and the eigenvalues and absolute value ones are z for some z. Okay, well, that's what you do. And by the way, how to do that is in my paper. In my paper on the classification of C-squared algebras of real rank 0 in 1993.